Okay, Bismillahirrahmanirrahim. So algorithmic complexity, right? So you can laugh, no problem. So abstract machine model, why we need an abstract machine model? So let's discuss it. I was talking about that, what I was talking about. First thing what you understand is that if we have to run a program, basically you are writing in some programming language. You're writing your program in a programming language. What's happening to it? You give it to the compiler, right?
Yes, sir.
But basically compiler will do nothing if you don't have assembler. Okay, keep this point into consideration. Now, in second year, we'll talk about this more now.
Yes, sir.
Okay, we were on here in the first year, but in second year we move on this. We have to do a lot of things about the assembler, which is basically working on a machine. The assembler is the guy who sees exactly the architecture of your machine. It sees the architecture of machine because no machines, machines are of different architecture. Intel machines, even Intel machines, a lot of families. You may have easily dual core system, single core system, quad core system, i3s, i7s, AMD, different architecture. This is Intel. We have AMD, okay, which is neck on neck with the Intel. They have totally different architecture. Is it? How their registers are arranged, how they work, their instruction set architecture, how they work. Every processor has its instruction set. What is it? Has its?
Instructions.
Called ISA, instruction set architecture. So every machine has its own language basically. Like for example, this house has a kitchen. Okay, does that mean how we arrange our utensils, how we cook, how we do things in our kitchen? Will that be same in your house? Definitely no, because that's different architecture. So to work in your kitchen, we need instruction set architecture of your kitchen like that. Similarly, to work on this machine, we have to make our programming language, what we have written, exactly in the same architecture. What kind of registers we have, what kind of instructions we have. Maybe, for example, someone has a circuit of, for example, multiplication circuit. We have multiplication circuit. You plug in values, it will output you the multiplication of that. Some machines don't have multiplications, but they have only error circuit. They have only what? And they have but instruction set in such a way. You say 2 cross 4, it basically in doing 2 plus 2 plus 2 plus 2. Using the error circuit. So that means we are implementing multiplication using error. So that means they will not have same instruction set architecture. They will have different instruction architecture. That's why compiler basically generates object code. And that object code is not machine language. Okay? It gives that object code to the assembler. Because assembler on one side is seeing the compiler, and on one side is seeing the architecture. It knows the architecture, exact architecture of that machine. So what that means is, if you have written a code, okay, that compiler basically converts that into the object code, and assembler takes the object code and makes it into assembly code. Now that will be in accordance to the machine, what we are talking about. This is very important point I'm talking about. That what does that mean is, if you have written some code, some program, you compiled it, okay, assembler will make the assembly code and then link it, linker will come up and link all the libraries. It will make an executable code, exe, is it? Because first if you write a programming language, some language, okay, whatever language you choose, you write a code, that is given to the compiler, that will generate the .obj, object file, it's given to the assembler, that comes .asm, assembly code, and the linker comes up, okay, which links all the libraries, and in the end it becomes executable code, exe. But this executable code, if that means if I have made the executable code, okay, which is running, it will run on this machine only. But if you try to run this on another machine, it will not work. It's like what programs we are implementing in our kitchen, it will not work in your kitchen. Does it make sense what I'm saying? Does it make sense? So that's what is the point. That architecture wise your machine will be different. Now, what we are actually, our topic is, what we are talking about is that is my algorithm better than algorithm B? Is algorithm A better than algorithm B or not? That's the main funda of this topic, is why we have abstract machine model. Why we need asymptotic notations. We'll discuss them tomorrow, but today you get an idea why we need asymptotic notations. You getting me? So I'm saying algorithm A is better than algorithm B. What are the performance measures? What are the criteria? What are the conditions under which I'm saying algorithm A is better than B? So differently which comes to mind is one is speed, and second is space or scalability. Speed means execution time. Okay? So I'm saying algorithm A is, so what is this? Efficiency. Which algorithm is efficient? Algorithm A is efficient, algorithm B is efficient. So I'm saying, hey, I want to see if it's efficient, let me check in the speed, execution time. How much time it takes to execute the particular code, that algorithm. You implement that algorithm in a program language, right? And just see how fast it goes. What time it takes. Okay? For example, you will use a method like current time dot millis. This method you will use to try to see how much time it will take. But this current time dot millis actually depends on the clock speed of a processor. Clock speed of a processor. That means I have written a program on a particular machine. Maybe that's highly fast machine, super scalar architecture, and highly parallel machine. Okay, what's called MPP, massively parallel processors. Maybe I have 1,000 processors. Okay, working in tandem, and I'm running my program on that machine. And somebody else developed another algorithm for the same problem in some other part of the world, and running but on the machine which is very slow. He says, hey, he run the current time of millis, and his time comes up very big. My time comes up very small, and I'm saying my algorithm is better, but it's not. Why it's not? Because basically it's a machine. But maybe my algorithm is better. I don't know. I'm saying it might be machine faster, but at the same time my algorithm may also be better. But I don't know. So we need something to measure the algorithm which is machine or dependent. Machine independent. Okay? That's what's called as abstract machine model. What is scalability here? What is talking scalability? Size. Yes, with the increase in the load. With the increase in the load, what do you say? Or input size. It should not fail. Because some algorithms work better when they're shorter inputs, but they fail when the input goes large. But we have to understand that our algorithm should not fail. It should be robust when the inputs are high. When the n input size goes high, it also fares well. So robustness is not only seen when the input size is low, when the input size is big. Otherwise, you say many times, hey, because one thing is data size, one thing is code size. Okay? We say code size, okay, no problem. We have got a big hard drive, terabytes of hard drives these days, and we got big RAMs these days. Actually, RAMs, not about hard drives. Actually, RAMs, when we execute program, it's all in RAM. So we say, hey, we have got huge RAMs, even the cache and increasing day in and day out. And levels, level 1, level 2, level 3 cache. We'll discuss then in computer organization, architecture, all these things. And we'll take up some modern processor also. Okay? Not only with syllabus, but modern processors also. We'll discuss those processors also. Okay? But we say, okay, RAM is huge these days. No problem if you have some 2 KB, 3 KB size of your program. Is it? Line of code. If it is more, no problem, because we got a big RAM. But the question is not that. Question is about the input size of data. We're not talking about the code size. We're talking about the input of data. Okay. For example, sort array. Okay. Of sorting code, same. For loop, 2 for loops, for example, nested for loops, bubble sort, whatever, insertion sort, or merge sort, whatever you do. Some few lines of code that's same. But for I is equal to 0, whatever it takes. Code is same. Okay, say for some 10 lines of code. But the data size, will tell us which algorithm is better. Because the data size n is, say for example, 10,000, bubble sort, it will, it will boil. It will boil. So we need some other algorithm than bubble sort, right? Is it? Because if it is, say for example, 10,000 size of array, bubble sort is an algorithm complexity of big O of n square. So that will be huge. So we need something which is logarithmic, complexity of logarithmic, which is shorter time. Is it? So that what I mean is the data size. That's what size means actually. Oh, I'm rubbing it. That's what scalability means. Is it not the code size, but the data size, not the program size, data size, the input data. Okay, on जिसके ऊपर आप complexity कर रहे हो, जिसके ऊपर आप processing कर रहे हो. You getting my point? So we have two important things. One is the speed. Now speed. How come we say speed? What speed, man? What speed? Because that will give the process speed. Okay, that your clock speed of a processor. That will not tell us exactly how your algorithm is. Is it better or not? Does it make sense what I'm saying?
Yes, sir.
So we need something what's called abstract machine model. We need what? Abstract
Machine model.
and sit down by what's called as asymptotic notations, which we'll take tomorrow in detail. Okay? I've given just an idea today. What is this? To remove all the machine dependent things, throw them off. Let us see a simple algorithm to see the bigger in the just tell me, help me out in a program. I'm not a program here. Just a function that tells us which one is the bigger in 100 array elements. In 100, say I got a array size of say 100, and I got elements in it. Okay, I've already done. Maybe elements are filled in it. I want to say which one is bigger. How I do that? How I do that? This is going on. I will deem this as my bigger. Is it? Then I compare. Compare. How I do that? Just tell me. Maybe I will say I will have a variable called big is equal to AR of 0. Okay. Then I run for I is equal to 1, I less than 100, I plus plus, because n is 100 here, input size is 100.
Less than equal to.
Mm-hmm. 0 to 99 can be.
1 to the
Because I have already L of 0 with big hai na? This I am done. I consider this as my big, that's here. So I run from here up to 99. Up to 99.
Yes, sir.
Is it 0 to 99?
0 to
Okay. What I do? If
A of I is greater than big, then big is equal to A.
Yep. If A of I is greater than
Big.
yep, then
Big is equal to A of I.
I will write then, huh? Then
Big is equal to
big is equal to A of you syntax whatever. This is valid syntax of VB. If we write then, if then else, big is equal to 5. If you don't want to then do C, if you want to go to C, then do this, whatever. Okay? I'll do that. At the end, whatever will be in the big is my what? Then you can write or print or whatever you say, print this big. Print this big. Is it? For example. Print this big. If I see how many steps it will take. How many?
steps it will take.
Getting my point? Because what we do is, we do not say what time it take. We move from this to say how many steps we have. Okay? Well, this is outside. You getting my point I'm saying? Little difference. I was saying how much time my algorithm will take. I was running starting run stopwatch. Start algorithm. Okay? Maybe current time per millis. Huh? Current time per millis. I said I run this method, which will tell me start, run also current time millis, stop program and stop the current millis, and it will tell me how many time. But that was basically the processor time, because clock speed of your processor was very high. That will elude you in deeming that your algorithm is better. Does it make sense what I'm saying? Get an idea today. If you're not, we are technically perfect today, but get an idea. That's the whole motto of today's lecture. Get an idea why we have asymptotic notations. Tomorrow will be more technical. We'll go more mathematical tomorrow. Tomorrow will be all math. Okay? Because we will see the formulas and all that. We'll try to derive things. But today, just an idea. You getting my point I'm saying?
Yes, sir.
Just stop me and ask if you have a problem. So, this what I'm saying here is I am not start algorithms, stopwatch, and just end and see this time. That's nonsense, because that will be easily the processor. Is it? That will be easily the clock speed of your processor. This may be, this may be run by the dual core system. You may have quad core system, which is breaking this into the chunks, and one processor doing this chunk, another processor doing this chunk, another processor this chunk, and bingo. They do it so fast. And you say, hey, my algorithm better, but it's not, never. You can never say. We need a clear understanding that is our algorithm better or not. So what we do is, we say how many steps. We forget about how many time, what time. We say how many steps your program has, your algorithm has, how many steps it has. That's a better thing to say. Okay? But it still has a problem. Because a particular, whatever you write in a programming language, that is be converted into the machine language. Is it? Basically that machine language, it is the assembler, I told you, is the assembler who converts the object code to the assembly code. And assembly code is like this. For example, we have add x1, x2, x3 means add x2 and x3 and drop it into the x1. Okay? That has two steps. Even if I say add x1, x2, it is two steps. That means add x1, x2 and drop it into x1. Add x1, x2, this is actually, some machines do like this. Add x1, x2 and drop in x2. But if you talk about your syllabus is 8086 processor, its machine instructions like this. Add x1 and x2, the registers. They're what?
Yes,
And put it into the x1. It has two steps. Different has two steps. It has what? Multiplication. If we have multiplication circuit, we say mul. These are called mnemonics. They're called what?
Mnemonics.
P-N-E-M-O-N-I-C-S. P is silent. Mnemonics. This is what in assembly language we have, the mnemonics.
Yes.
Mul, same, x1, x2. Multiply 2, put in x1. But if you have multiplication unit, if you don't have multiplication unit, then it will add, it will take a lot of steps.
Yes, sir.
Okay? There's 2 raised for this much of steps. Is it? I say 2 cross 6. What are we still doing? 2 plus 2 plus 2. 1, 2, 3, 4, 5, 6 times. So in multiplication unit, if you it will have a 1 step. In addition, if you do the same thing with the addition, it will have 1, 2, 3, 4, 5, 6 steps. Is it?
Yes, sir.
So, isn't this machine what I'm talking about? A machine having multiplication unit, a machine having this much addition unit. So in a machine, you are trying to run the same, wherein we have a one instruction, multiply. Okay? And you are running on a machine which is having an adder. If it is 2 into say 10. In a machine which has a multiplication circuit, it does in a 1 step, bingo. In your machine which is having an adder, not the multiplication unit, it will do the same thing, the same line of code in 10 steps. And I'm saying my algorithm is not better, it takes 10 steps, it takes so time. And another guy says, hey, my algorithm is better. My algorithm is good, it takes just a bingo. Okay? But basically we are both same, we are doing multiplication, both guys. We have written 2 into 10. Both of guys have written same thing, 2 into 10. And when I try to run it here, and I try to run it here, on another machine, he is telling me, hey, my speed is so fast, my algorithm is so good. And this guy is saying, my algorithm is not good. But actually it's not algorithm, it's a machine. Do you understand this point?
Yes, sir.
It's actually the machine, not the algorithm itself. So this thing is not a clear indication of which algorithm is better, which algorithm is efficient. Basically we say efficient, technically. Okay? So what I say is, don't do this. If you have multiplication, say it is 1 unit. If it's addition, say it's 1 unit. Okay? Even though addition takes 2 steps, okay? It takes 2 steps. Don't do 2 steps, say 1 step. Or everything 1 step. So now you say addition, 1 step. Multiplication, 1 step. Whatever the machine is, you forget about it. Is it?
Yes.
You forget about the machine. Will it do this way or that way? Forget about it. Just say 1 step multiplication. That gives you clear indication of the algorithm. But we are not yet done, because there are many things which will come up. We'll forget them also. To reach here, asymptotic. I will come to this point. Okay? So I will finish this, we'll understand asymptotic. Now, I think we have successfully removed the machine. We have successfully come to the abstract machine model, right?
Yes, sir.
Wherein what I'm doing? Wherein I am doing what? I have removed the machine. I said no clock time, don't use stopwatch, forget about it. Don't use your processor speed, forget about it. If it is card core, whatever it is, it doesn't matter. If your steps in a program are 4, if you run it on a particular quad core machine or you run it on a single core machine, no problem, because we say our machine is step 4. Now your quad core machine may have broken it into the 4 chunks and given to the 4 processors and done it in 1 clock time. Okay? If you have 4 steps in a machine, if you have 4 steps in a machine, your quad core may have 4 processors. For example, it will break your program into 4. Okay? Give to every processor 4. Gives one job. It will complete in a 1 clock cycle. Your single core will do it in a 4 clock cycle, and you say, hey, my algorithm better, 1 clock cycle. He says, no, my algorithm not better because 4 clock cycle. But in fact, it's both same algorithm. Because it's the machine. So we removed that. We said, how many steps you have? Forget about the machine. He said 4 steps. He said I have 6 steps. So definitely 4 steps is better than 6 steps. So how many steps we have? Does it make sense what I'm saying?
Yes, sir.
So for I is equal to, if you see this, if you take from here, if you take this, okay, and try to see how many steps will it take. How many times this will run? I is equal to 1.
1 time.
It will run 1 time. Is it? How many times this will run?
99.
99 times. Is it? In fact, 98 times or 99 times?
99.
Because I is less than 100? Because it starts from 1?
1 to 99.
1 to 99. So it is n minus 1. It's n minus?
1.
It runs n minus 1 times, it runs 1 times. It runs also how many times?
Minus 1 time.
Is it n minus 1 times?
N times.
Or n times?
N times.
It runs n times, exactly. Because at the end it will say,
Okay.
yeah,
Again increment.
then this will false, okay? How many times this will run?
तो फिर वो भी कंडीशन n टाइम्स होगी ना शायद केस लास्ट थी वो बस प्लस प्लस की कैसे भी चेक
1 to 99 चलेगा नहीं? Less than तक करेगा ना काम?
Execute होगा.
1 to 99 तक ही ट्रू हो जाएगा उसके बाद भी शायद
Let us make it smaller. Let us make it smaller to understand. Let us make it 10. I is 1. It will run 2 for 2. It will run for 3, 4, 5, 6, 7, 8, 9. Is it?
9 तक चलेगा
I plus plus.
फिर
I
से
plus?
चेक होगी ना कंडीशन
एक मिनट. I plus plus. I कितना बनेगा?
10.
10. Okay? Yes. How many times this is?
10.
10 times. So it's 9 times. Because at the end it will still chuck when the condition is false. So it has to run.
Yes, sir.
This one
And
also n times or n minus 1 times.
and times.
I is 1. Okay. When I is 1, it increments. Make it 2. Okay. So here is 1 time. 2 times, 3 times, 4 times, 5 times, 6 times, 7 times, 8 times,
9.
9 times.
And minus 1.
This will be n minus 1 times. Yeah?
Yes, sir.
So now whatever size it is, we don't care. If it is n, whatever the n is. So 1 times, n minus 1 times. And this guy,
And minus 1.
n minus 1 times. Is it? This will run comparison n minus 1 times. The last time it will not run.
Yes, sir.
Okay, because when the condition is false, it will not run n minus 1 times. If A of I is greater than big, okay, do it. big is equal to error of I. But if it is true, only then it will run.
Yes, sir.
Is it? Huh?
One time.
Why run times? It depends.
Yes, sir.
Now this guy depends. So that's why we have three things. We have best case,
Worst.
we have average case, and we have worst case. Is it?
Yes, sir.
अगर पहला ही बिग था तो ये तो कभी चलेगा ही नहीं. मान लीजिए ये 20 है 1 2 3 4 5 air of 0 में big मैंने डाला. You got a big in the air of 0. Air of 0 in the big. That's 20 is in big. फिर हम कंपेयर कर रहे हैं क्या ये इससे बड़ा है नहीं है तो कभी चलेगा ही नहीं.
Best case.
ये कभी चलेगा. It's the best case. But best case is bogus. When you say algorithmic complexity, we don't worry about best cases. What we worry about is worst cases. Okay? We don't say best case, hey, this is good. We don't need that. That will not give us how better you are. because best case में तो कोई भी होता है. मैं कहता हूँ अच्छा लड़का है, ठीक है, क्योंकि अच्छे से बैठता है. वो उसमें नहीं, उसमें देखना जब लड़ाई होगी उसको क्या करेगा ये. अगर उसको किसी के साथ लड़ाई होगी, how cool it is, he is. You're saying, hey, this guy is cool. We don't see in a normal situation. We have to see it in a, and he's playing football, blood is rushing, and somebody gave him पीछे से उसने फाउल दे दिया इसको. जब वो नीचे से उठेगा, मुझे देखना है कि इसकी कूलनेस कितनी. शायद मुश्किल वापस करना. Yeah, I'm playing football these days. You know, there are many cool guys. I say cool. There's one guy who was very cool. There was no normally push. So was the boy. So was the ball football कितना? So was the भी बना क्या उस? दोनों में फाट हुआ. Really, he was not playing football. He was just trying to see कि मैं इसको कब पकड़ूंगा और मैं ये करूंगा इसको. हाँ? So we don't have to see he is cool because he was normally very cool. When I was talking to him, he was so good. But not in those conditions. You have to see in harsh conditions. You have to test him under the worst conditions and see how cool he is. Is he cool or not? Then you can see. इसलिए कहते हैं कि अगर बंदे को देखना होगा तो सफर में देखो. ठीक है? सफर में पता चलता है कि बंदा असल में कैसा है. अभी आपको कोई बंदा अच्छा लगता है, it's good, he's cool, but you never know. Just go with him on the journey and you will understand how he is. You getting me? So in a worst condition में देखना है कि ये बंदा कैसा है. So worst condition में देखना है algorithm कैसा है. Best case में क्या देखना? Best case is bogus, right? And worst case, average case is sometimes, you know, we say average case means what? कि कभी ये तो कभी वो then divided by no arithmetic, like what do arithmetic mean? We say averages. But the best thing to judge an algorithm is the worst case.
Worst case.
जब array उल्टी हो sorted, तो 20 थे हो,
5.
ये 50 हो यहाँ पे, ठीक है, और ये इससे भी बड़ा हो, ठीक है, ये 30 हो, 40 हो, 50 हो, 60 हो, और ये 80 हो.
एक से बढ़कर.
This is reversely बड़ा, what you can say. So इसमें हर बार ये चलेगा. हम उसकी बात करेंगे, हम इसकी बात करेंगे वर्स्ट केस की. ठीक है, वर्स्ट केस में आपने कहा उससे हमें पता है कि इससे हम खुद बदतर आज नहीं है. ठीक है, इसको ना बदतर से अबतर से क्या बदतर क्या होना है और दो होता है वो. हाँ, बद से बदतर अबतर आज. ठीक है, उसने रिकॉर्ड सुना था ना वेद के आगे से बोले. ठीक है, तब सूरज में कैसे चाहिए, तब तक सूरज में चाहिए हर बार. अगर ये n-1 चला तो ये भी n-1 चलेगा. इज इट? जब ये बाहर निकलेगा, जब ये खत्म होगी ये लूप, तो इसको बिग में वो होगा जो सबसे बड़ा होगा. ठीक है, सो यहाँ पे कौन होगा? अक्षय कुमार सबसे बड़ा खिलाड़ी. In the big we will have the 80. Is it then going to print it? This will be one time. This will be
one time.
तो कितने स्टेप्स आपको कूल लगे इसमें? सिर्फ इसकी बात कर रहा हूँ मैं. 1 plus n times plus n minus 1 times plus
And minus one.
plus.
Plus one.
So plus and minus 1 equal.
Okay, I'm gonna plus and minus one more.
Plus 1.
ठीक है? Add them together. How much is this? Ak en, 2 en, 3 en, 4 en. This is 4 en.
4
Plus 1. 1 और 1 खत्म. ये और ये खत्म और -1. 4 और माइनस. So हमें ये कॉम्प्लेक्सिटी मिली इसकी. ठीक है. फिर हम क्या कहते हैं? अब हम एसिम्पटोट के ऊपर आते हैं. ये मेरी निकल गई इसकी कॉम्प्लेक्सिटी. स्टेप्स. कभी आपको अभी तो हमें निकला 4n - 1. क्या निकला? बात समझो. इस वक्त बाकी कल होगा. 4n - 1. कभी ऐसे 7n square - 2 plus 3 whatever. कभी निकला 2n square plus 3n plus 2. कुछ ऐसा निकला हमें. मेरी बात तो सुने. हम कहते हैं कि देखिए भाई कि जब इनपुट बढ़ जाएगा, जब इनपुट अगर आप इसकी बात करोगे 4n - 1, अगर n छोटा है, अगर n से मान लीजिए n 0 है. n क्या है?
0
ये n के वैल्यू है. यहाँ पे 4n - 1. अगर n 0 है, 0 into 4 is 0 - 1 is.
-1.
तब जाके जो ये बंदा है ये 100% ऑफ योर एल्गोरिथम है. 100% एल्गोरिथम ये है 1. अगर आपका n हो गया 1, क्या हो गया? 4 times n is 4 times 1 is 4 minus 1 that is 3. तब भी आपका जो ये 4 है, जो कांस्टेंट है, ये ज्यादा आपको इसकी में काम आता है. Then n tends to very huge. Say 200, 300, 500, 1000. ठीक है? तो फिर इस कांस्टेंट की कोई वक़्त नहीं रहेगी. इस 4 की भी कोई वक़्त नहीं रहेगी. The thing which is governing is this n. यहां आप देखें 2n square plus 3n plus 2. ठीक है? अगर n छोटा है, n क्या है? Say for example 1. 1 का स्क्वायर is 1, that is 2. 1 3 into 1 is 3 plus 2. So ये बिग टर्म ये आ रही है. The n छोटा है. लेकिन when n goes big, n goes say 20, say 10. 10 का स्क्वायर is 102 is 3 into 10 is which one is big? So जितना n बढ़ जाएगा, इस 3n इस 2 की कोई वक़्त नहीं रहेगी. ये दरअसल ये टर्म जो है और इसमें कौन n स्क्वायर जो है ये डिसाइड करेगी आपके एल्गोरिथम बेटर है या नहीं है. सो हम ये कहते हैं एसिम्प्टोटिक में कि पहले आप स्टेप्स निकालो. कंप्यूटेशन स्पीड, प्रोसेसर क्लॉक स्पीड, फॉरगेट अबाउट दैट. नंबर 1. नंबर 2 वी से see in those steps which one is the governing term. Okay? So अगर चाहे कुछ भी हो, this algorithm is better than this algorithm because it's n square. It is n. There's lesser steps than this. When n goes high. और इस एल्गोरिथम में n स्क्वायर आपकी गवर्निंग टर्म है. इसमें n स्क्वायर आपकी गवर्निंग टर्म है. इसमें n आपकी गवर्निंग टर्म है. Drop 4, drop 1, drop all this stuff and take n square or n. Drop all other constants. What are the constants you may have? Those constants may be because of your processor. Those because of the machine. Other constants which will govern the speed of your algorithm. Forget about them. Just tell me one thing, okay, which will be used to see the worst case scenario of your algorithm, and that is this governing term. Okay, so if I have the steps like 7n square plus 2 minus 3, 2n plus 3 like this, I will say this is big O of n square. The complexity of this is big O of
n square.
You getting me? Forget about others. Let us take an example to finish it up. One example today and we finish up. We come up tomorrow and do it more technically. When we discuss big O, big omega and big theta. Okay? Let us do the bubble sort. Let's do what? I will give the idea about 3 sorts today because we have to do a lot of sorts. Bubble, heap, insertion, selection, merge, quick sort, a lot of sorts. Okay? Radix. We'll do all these. in searching linear and binary, and then see how they fare with our big O. Worst case scenario, what I'm talking about. Is it? Okay, now look here. We got bubble sort. How will we do bubble sort? We have, for example, an array. What we do is we compare these two. If this is big, this is not lesser. Say for example, if this is big, this is smaller, we swap them. Then I compare this with this. If this comes big than this, swap it. Compare this. If this comes big, we don't swap. Then this with this, swap if big, swap if big. So at the first round, the big will come here. Say for example, this is 20, 1, 11, 9, 5, 7, 13. So we go like this. Let it be like this. We go for the first round.
20.
We go for first.
Round.
Is 20 bigger than 11? Swap it.
11.
So what will happen?
11.
11 comes here, 20 comes
20
here.
comes here. Then 20 and 9.
Now, second iteration of a loop. Is 20 bigger than 9? 9, 5, 7, 30. Right like this. Is 20 bigger than 9?
Yes, sir.
Swap them. 11, 9, 20.
20.
Is 20 bigger than 5?
Yes, sir.
Next term. Swap them. 11, 9, 5.
5, 27 and 30.
Is 20 bigger than this?
Yes, sir.
Okay? Then is 20 bigger than 13?
Yes, sir.
Swap it.
20 now small.
Now in the first round, this is the first round. The bigger element is here. Okay? Now I don't take this. I have done with this. My next round starts from here to here only. Same thing. But here to?
Here on.
Is 11 bigger than 9? This is round. This was round 1. This was round.
1.
I go for round second. 11 bigger than 9?
9, 11.
Yeah. 9, 11.
11, 5,
5,
7,
7, 13. Then 11, 5 here.
9, 5, 11, 7, 13.
11 bigger than 7?
Yes. 9, 5, 7, 11, 13.
11 bigger than 13? Don't do it. Same. But iteration हो जाएगी. It will come here, हाँ? करेगा कुछ नहीं, swap नहीं करेगा, लेकिन iteration होगी. Now 13 next bigger element has come here. So I don't do this. My array remains this much. Okay? Round number third.
5, 9, 7, 11.
Is it? Which one is it? 9, 5?
9, 5, 7, 11.
ठीक है? मुझे क्या आ गया? पहले पोजीशन में आ गया 20. ठीक है? और दूसरे पोजीशन में आ गया
30.
again the same position. 9 greater than 5?
Yes, sir. 5, 9, 7, 11.
9 greater than 7?
No.
Why not?
Yeah, no. Yes.
9 greater than 11? No. Stop it. This is done. 11 is here. My next array remains this much. This is gone. Same situation. Is 5 greater than 7? No. Is 7 greater than 9? No.
No.
9
9.
has come up. This remains the array. Is 5 greater than 7? No. So that's it. 5, 7. Is it? So 7 comes here, 5 comes here. I'm done in sorting my array. Now how much steps will it take? How many rounds will it take? It will take first round, second round, third round, and fourth round. Is it? और इंटरनली कितनी बार करना है? इस राउंड में कितनी बार मैंने किया? 1, 2, 3, 4, 5, 6 बार. Is it? क्योंकि 1, 2, 3, 4, 5, 6 एलिमेंट थे. So I have to run from this one to whatever the value n is. How big is it? It is. Is it? है ना? और दूसरी बार कहाँ तक करना है? हाँ, एक कम.
5 rounds.
हाँ?
5 rounds.
Okay.
And mine.
One round here. Second round is this guy. Third round is this guy, and fourth round is this guy.
Sir, 5 or 7 again.
Yes. So 5 rounds. Is it? So what I am doing, I am running this one up to the end. This will be my outer loop. This will be what?
Outer loop.
You understand how it does?
Yes,
Yes,
sir.
sir.
It compares the two. That's why it's called a bubble. We call it bubble. In the first round, 20 bubbles on the top, biggest number. In the second round, 13, which is the next bigger, bubbles on the top, and so on. That's called bubble sort. It's called what?
Bubble sort.
It is Wahiyat sort because it takes a lot of steps to do things. We have much better things which we'll do, which are logarithm. So how we do this?